Let's calculate the pH of a solution before starting a titration. In order to calculate the pH of a solution, in this case acetic acid solution, we must find what the concentration of the hydronium ion is at equilibrium. Considering we're just starting off with a 0.1 molar solution of acetic acid, we're going to have to go through and do the equilibrium calculation. In order to do so, I need to first write out my balanced chemical equation, which in this case is the dissociation of acetic acid into hydronium ion, H+, and acetate ion, C2H3O2-. Now that we've got the balanced equation, we can begin to create our ice table. The initial condition is that we have a 0.1 molar solution of acetic acid. And since we don't know anything else about the solution, we're going to go ahead and say that the hydronium and acetate ions have no molar concentration. We now allow our equilibrium reaction to begin, allowing things to change. In this case, there are no product concentrations, therefore their concentration will increase during the course of this reaction. And since they both have a coefficient of 1 in the balanced equation, for every H+ you create, you also create an acetate. Likewise, we consume an acetic acid when we create those hydronium and acetate ions. So the change in this case is going to be positive X for the products and negative X for the reactants. At equilibrium, we now combined our initial and change terms to get the equilibrium concentrations. Now, when we go to calculate the pH, we need to know what the value of X is for the hydronium ion. In order to find that, we must set up our equilibrium expression. In this case, equilibrium Ka, this is an acid dissociation constant reaction, and therefore we use Ka, and that's going to be equal to H+ concentration over the acetate ion concentration all over the acetic acid concentration. There we go. Now, we're ready to use our equilibrium concentrations and the acid dissociation constant. Now, for this particular reaction, you would have to go and look up what Ka is. However, I've very conveniently written it down here, and I know that Ka for this reaction is equal to 1.8 times 10 to the minus fifth. I also know at equilibrium constant, or at equilibrium, we had X amount of H+, we had X amount of acetate, and that's all over 0.1 minus X at equilibrium. Now we just have to go through and solve for X. In this particular case, I'm going to go ahead and treat X as a very small number. That is, I'm going to use the 5% rule for this problem. When using the 5% rule, really the benefit of doing that is that you get to treat this term as if it were 0. So we're just going to go ahead and scratch that out. This works a lot of the time, but not 100% of the time. When the equilibrium constant and the concentration are fairly close in value, you're likely to get an increase in error, and we can go through and look at whether or not this was a good decision to make after we've done the problem. So, I now have X squared over 0.10 equal to 1.8 times 10 to the minus fifth. Now we just need to go through and solve for X. So taking the equilibrium constant and multiplying it by 0.1, I get 1.8 times 10 to the minus 6, and that's equal to x squared. Now I can take the square root of both sides to solve for x, and I get 1.34 times 10 to the minus third. All right, well, let's see if this was a wise decision to treat x as a fairly small number. That is, we're going to go back and verify that the 5% rule was a good choice to use. To do so, what we do is we take our value of x, 1.34 times 10 to the minus third, and what we're going to do is we're going to divide it by the concentration we originally had of the acetic acid, 0.10 molar. And then we're going to change that into a percentage, so we're going to multiply it by 100%. So if this value is less than 5%, then we are okay with this. And when I do so, I find that there is only 1.34% error in this value of x. So the 5% rule was appropriate to use here. So now we know x is 1.34 times 10 to the minus third, and that is equal to the H plus concentration. So H plus equals 1.34 times 10 to the minus third. To find the pH, we take the negative log of H plus. So negative log of 1.34 times 10 to the minus third, and that is going to equal 2.87. So the pH of this solution is 2.87.